We drive past the most critical, life-saving civil engineering every single day, and we barely even register it. I'm talking about road barriers, the guardrails, those big concrete dividers. They are the silent guardians of our highways.
It's so true. I mean, most people just see a piece of metal, but it's really an intricate system. It's engineered to manage kinetic energy in a very precise way.
So this isn't just a fence.
Oh, not at all. It's an active safety component.
Well, our mission today is a deep dive into the physics and the material science behind these roadside heroes. We're going to unpack how engineers tailor everything from flexible steel cables to rigid concrete to absorb impact.
And really, to reduce the severity of a crash and prevent fatalities.
Exactly. We need to know what's in the toolbox, how they choose the right barrier, and the testing that proves it works when your life is on the line.
And I think the biggest takeaway for you, the listener, is understanding that these systems are designed to work with your car's safety features.
With the crumple zone, the airbags.
Yes. The barrier takes the hit. So the G-forces on you, the occupant are survivable, the barrier gets damaged, you get a second chance.
Okay, so let's start right at the foundation. How do these things save lives without just, stopping a car dead, which would be catastrophic?
Right, and that's the key. It's a little counterintuitive. The goal is not to stop you abruptly.
Because an instant stop.
An instant stop means all that kinetic energy gets transferred directly to the people inside the car. That leads to severe, severe injury. The real solution is controlled absorption.
Which brings us to the first big mechanism, deformation. You see this with steel guardrails all the time.
Precisely. When a car hits a flexible barrier, it's engineered to bend, to stretch. Sometimes the posts are even meant to break away.
So that bending and flexing,
Yeah.
that's the barrier doing its job.
That is the barrier absorbing a huge amount of the vehicle's energy, but over a longer period of time and distance. It reduces the rate of deceleration.
It slows down the stop.
It turns a sudden impact into a more gradual event. It's a programmed surrender, in a way.
But wait, if the barrier's designed to essentially fail by deforming, doesn't that make repairs incredibly expensive and time-consuming?
That is a brilliant question.
Is that why we still see so many concrete barriers in high-traffic areas?
Yes, that gets right to the heart of the engineering trade-off. Deformation is fantastic for occupant safety, but it's a nightmare for maintenance budgets and traffic downtime.
Okay, so that friction leads to the second mechanism,
Controlled redirection.
the guiding principle.
Exactly. Instead of stopping the vehicle, which causes high G-forces and barrier damage, many barriers are designed to redirect it smoothly and safely back onto the road.
So they're angled or curved to sort of steer the car away from danger.
Yes, the car hits at an oblique angle, and the barrier converts that forward momentum into lateral momentum. The vehicle just slides along the hazard instead of hitting it.
And this whole redirection idea is why the designs had to evolve, right?
Right.
I remember reading that some of the older barriers were actually creating new fatal problems.
That's a critical point in safety history. Early barriers sometimes acted like spears.
Horrifying.
Yeah. If a car hit the exposed, sharp end of a guardrail, it could penetrate the cabin. The push for safety then introduced energy-absorbing end terminals. They crumple like an accordion and breakaway posts.
So the posts themselves are designed to shear off.
They snap off cleanly, so the barrier doesn't become this fixed, rigid object that causes more harm.
It's a whole integrated system then. Your car's crumple zone, the airbags, the barrier's deformation, its redirection. It all works together.
It does, which leads us perfectly into the engineer's barrier toolbox.
Because they have a lot of different tools for very different jobs.
Absolutely. You can divide them by their strategy, deflection, rigidity, or high absorption.
Let's start with the classic steel guardrails. The W-beam you see lining almost every highway.
The workhorses. They're all about deflection and deformation. They absorb impact by bending and stretching, and their main job is to contain a vehicle and redirect it.
Then you have the total opposite, the concrete barriers. The rigid titans.
Right, and you see different types, like the Jersey barrier, the F-shape, the single slope barrier.
And they're all pure redirection devices.
Pure redirection. They are designed for minimal damage after an impact and are used where you absolutely cannot have a vehicle crossing over, like on a median or a bridge.
Okay, you mentioned the different shapes. To a casual driver, a Jersey barrier is just a big block of concrete. What makes the F-shape a big improvement?
It's all in the geometry of the slope. It's a huge technical nugget.
Unpack that for us.
Okay, so the original Jersey barrier has a slope that can sometimes grab the tire. It can cause a vehicle to vault to roll up the face and potentially flip over the barrier.
Oh, wow.
Yeah, or at least cause massive damage. The F-shaped barrier changes that.
How?
It has a slightly different, more gradual, lower slope. That geometry lifts the vehicle just a little bit upon impact, which reduces the load on the tires for a split second.
And that little lift prevents the climb.
Exactly. It prevents the vaulting but still achieves redirection, and with much less damage to the vehicle. It's a huge safety refinement.
That's fascinating. A tiny change in geometry completely changes the outcome of a crash. So at the other end of the spectrum, you have the really flexible ones.
Yeah.
Cable barriers.
The wire rope systems. Yes. They are probably the best at energy absorption.
How do they work? They look so flimsy.
They consist of multiple steel cables strung along lightweight posts. They work by flexing and stretching over a very, very long distance.
So the give is the key.
The give is everything. They can stretch for tens, even hundreds of feet. That dissipates a colossal amount of energy, which makes them amazing for preventing high-speed cross-median crashes in wide medians.
But the downside must be maintenance.
A big downside. They need a lot of repair because they deform so much.
And of course you have the temporary ones, the water-filled barriers in construction zones.
Right. They're movable and rely on the mass of the water to slow vehicles down. But that brings us to a really critical distinction.
Okay.
The difference between a continuous barrier, like a guardrail, and an impact attenuator.
You mean a crash cushion?
Yeah.
What separates a guardrail, which is for side impacts, from, that row of giant yellow barrels you see at an off-ramp?
Purpose. A guardrail manages oblique strikes along a path. A crash cushion, or impact attenuator, is built for one thing and one thing only.
Which is?
To safely stop a vehicle that is hitting a fixed object head-on.
So you find them at the end of a concrete median or in front of a bridge pier?
Exactly. Or toll plazas, any specific danger point. They are basically engineering the perfect crash.
Turning a catastrophic stop to a controlled accordion squeeze.
That's a perfect analogy. They use crushable materials, hydraulics, things designed to collapse in a controlled sequence. They're true shock absorbers for the road.
It's clear that engineers aren't just picking the cheapest option. So what goes into that decision? What dictates whether a road gets a steel beam, a concrete wall, or a cable system?
It's a very sophisticated trade-off analysis. First is traffic, volume, speed, and the mix of vehicles.
So a highway with lots of heavy trucks needs something stronger.
Much stronger. You need a robust barrier to handle those immense impact forces. A quiet, local road might use something lighter.
Then you have the physical space, I imagine. Road geometry.
A sharp curve or a steep embankment might call for a flexible, energy-absorbing barrier. But a bridge deck, where space is tight and repairs are a nightmare, usually gets a rigid concrete parapet.
And that brings up maintenance again, the life cycle cost.
A huge factor. Concrete is expensive up front, but it lasts a long time. Cable barriers are cheap to install, but they might need repairs several times a year.
And every repair means closing a lane, which creates its own hazard.
Precisely. You have to calculate the total cost over 20 years, including the cost of traffic disruption. In a busy city, the resilience of concrete often wins just to keep traffic moving.
So once the system is selected, they don't just hope it works. This is where their rigorous testing standards come in.
It is anything but guesswork. In the U.S., the gold standard for validation is compliance with the Manual for Assessing Safety Hardware.
MAH.
MAH, correct.
Yeah. Now, MAH doesn't just test if the barrier breaks, does it? It's about occupant safety.
That's the key. MAH sets up a series of full-scale crash tests with standard vehicles at specific speeds and angles.
And they have different levels, right?
Yes, you'll see ratings like TL3, TL4, and so on. A typical highway needs a MAH TL3 rating. That means testing with a small car and a pickup truck hitting it at 62 miles per hour.
So that's the baseline.
That's the baseline. But a major freight corridor might need a MAH TL5 rating. That test involves a heavy single-unit truck. It's a massive difference in the forces involved.
And they have to prove the vehicle stays stable, nothing enters the cabin.
And that the G-forces on the crash test dummies are within survivable limits.
But before they do these incredibly expensive physical tests, they're using computers, right?
Oh, absolutely. The first step is computer simulation using finite element analysis, or FEA.
So they can virtually crash test hundreds of designs.
Exactly. Identify weaknesses, refine the geometry, and save millions of dollars before they ever build a physical prototype.
So all this data, virtual and physical, what's the actual proven impact on our safety?
The impact is profound. I mean, road barriers are one of the most effective tools we have. The Federal Highway Administration reports that installing median barriers can reduce cross-median crash fatalities by over 90%.
Over 90%. That is staggering.
It is. They prevent crossovers,
Hmm.
they reduce runoff road crashes, they protect us from fixed objects. Even the reflective tape on a barrier provides crucial visual guidance at night.
So this knowledge directly impacts our defensive driving. What are the key takeaways for us behind the wheel?
The most critical warning, even with modern designs, is to never, ever connect head-on with the end of a barrier.
Because you're hitting the strongest, most rigid point of the entire system.
Precisely. You're getting the absolute peak deceleration force. If a collision is unavoidable, you want to strike the long, continuous section of the barrier at an oblique angle. Use its redirection function.
And in terms of everyday driving, maintain that space cushion, especially near concrete walls.
Yes, a concrete barrier has zero give. If you hit it, you are coming straight back into traffic, which can cause a secondary collision. Slow down in construction zones and be mindful of your space.
And a quick word for pedestrians and cyclists.
Stick to your designated paths. Those barriers are there to contain multi-ton vehicles moving at high speed. And wear bright, reflective clothing so drivers can see you near that infrastructure.
Well, this has been a true deep dive. We've gone through the material science, the physics. We know that deformation and redirection are the keys to saving lives, and that the MASH ratings are the gold standard for proving it.
And hopefully that knowledge changes how you see the road. But the sources are clear on one thing. For these systems to work, they need constant vigilance. Proper installation and continuous maintenance are non-negotiable.
A damaged barrier is an ineffective barrier. So, here's the final thought for you to carry on your next drive. If the effectiveness of these life-saving structures relies entirely on their condition, what is one observation you can make the next time you drive past a guardrail that tells you something about its current safety readiness? Are the posts straight? Is the cable taut? The state of that barrier is the state of your safety network.
Please like, subscribe, and get notified.